First of all, I would like to thank to all of you for listening to this presentation. My topic is Schwarz problem in a ring domain. This is a joint paper, actually. It has already been seen, published. So you may see some of the familiar parts during this. Well, we have 5 different sections. In the first part, in the actually first 2 parts, I want to discuss the problem in the unit disk, which was the preliminary form of it, and then we will go to the ring domain. The Schwarz boundary value problem in C may be given by this theorem, actually. In homogeneous Cauchy-Riemann equation, just I have to check these. Oh. Okay. In the unit disk, and as you see, this is the first order differential equation. Derivative is with respect to z bar. It has several conditions for the derivation of uniqueness. And in this theorem, we know that if f is in L1, gamma is a piecewise continuous, actually not continuous, but piecewise continuous. No, that is on the unit disk, gamma is continuous in the boundary, and then the Cauchy-Schwarz-Pompey formula gives you the solution, actually, in the final line there. That was the first order differential equation. For second order differential equation, you will naturally expect that the boundary conditions are increased, and roughly that is all what we can say here. We have, in our case, the second z bar derivative with respect to the second z bar derivative is equal to f we get and the proper conditions, and it is uniquely solvable. The solution is in this one. Now, actually, it is the second order differential equation. So roughly what we have done is we have started with the first order equation, and we have just introduced by repeating it into itself. Now, in these equations, the most important things are integral operators. If the integral operators are suitably chosen, then you can find the solution directly, almost directly, actually. In this page, we want to take the operator T1 tilde, that is a double integral of some quantity. That double integral of some quantity is actually the part of the solution of of first order differential equation. And we will see that it is also used for the higher order derivatives. Now, the operator we have here was T1 tilde. And what we know about this operator is that if you differentiate that T1 tilde f with respect to z bar, you will get f. And if you differentiate it with respect to z, then you will get a new operator, pi1f. Actually, pi1f is given in the next line. You can easily observe that T1 tilde is a weakly singular integral operator, and pi1 is strongly singular integral operator. Now, using iterative applications, you can find the integral operators corresponding to higher order differential equations. Now, this is actually for a kth order differential equation. Tk is obtained in this way, and you can easily observe that T0 for k is equal to 0, you will have f again. In the next theorem, we state that Tk tilde is actually the iterative applications of T1 tilde of k times. This was a good result, and it will be used. Now, we will need the properties of some operators. Tk tilde f has the following properties. The first one is if you differentiate it with respect to z bar, the order of the differential equation and the order of the operator is reduced. That is, Tkf differentiated with respect to z bar L times is Tk tilde, Tk minus L tilde f. And the important thing here is the function you are going to get here should also satisfy the conditions, boundary conditions on the problem. Okay, then we can proceed to derive the derivative of Tk tilde. If you want to differentiate the derivative of Tk tilde with respect to z, L times, and if L is less than k minus 1, then you get the formula given here by number 4. These are all weakly singular integral operators. But what we have here is Tk tilde differentiated with respect to z, k times. In this case, we get a strongly singular integral operator. That is, in the previous case, we have chosen this k minus 1 here to get the weakly singular integral operators. And then here, just take the order of differentiation, k is enough to get this strongly singular integral operator. Well, then we should know the properties of these operators. for the unit disk. Firstly, you will observe that pi k may be decomposed into two parts, t minus kk and pk. Those were discussed previously by Beger, and given the properties of tk, tmn type operators. And then here, we give a property of pi k, actually. For the pi k, first of all, if you choose f in LP, pi kf is also in LP, for p1 to infinity. And the next thing is that pi kf, the LP norm, is bounded. LP norm is bounded. And in particularly, if you choose L2 instead of LP, you can find that bound in Vikwa's book also. This is the bound. Now, these are the standard investigations or starting investigations for the Schwarz problem. You know, Schwarz problem is actually a subclass of Riemann or Riemann-Hilbert problem. Now, in a ring domain, what we have will be this thing. Firstly, we take the ring as R, that is, absolute set is in between R and 1. And the simplest problem here is first order again. The first order differential equation, Wz bar is equal to F, is given in R. We need the boundary conditions. On R, dr, the real part of W is given, and integral of imaginary part is also given at one point. We should be careful that the function gamma is a piecewise continuous function on the boundary. We will use it in most of the places. Okay. Now, using this integral representation, we can find the discuss the existence and uniqueness theorem for the Schwarz problem. The theorem is given in this way. Schwarz problem in R has a unique solution given by this formula 8. Be careful with the K1 and K2. Is a unique solution, but that solution is subject to some solvability conditions, and these are the solvability conditions. Using an induction technique, actually, we can find that this will be the solution we are looking for. The inhomogeneous Schwarz problem for higher order differential equation is dz bar to the nw is equal to f in a ring domain, subject to suitable number of boundary conditions, and we know that gamma sub j are piecewise continuous functions, and these are the solvability conditions. The last two lines gives you the solvability condition. That is the whole statement. Now, we should at least make believe you that the theorem may be proved easily. Let us start with the proposed solution. This will be the proposed solution since the nth order derivative of this function, w of z, will give you f. That is, the proposed solution is given by 11. Okay, now then to complete the solution, you know, we had the Cauchy-Riemann equation, so the boundary conditions should hold. Boundary conditions are obtained by the derivatives of w restricted to the boundary, that differentiations are with respect to r. Well, the S order, the order S of the derivatives are given in here. Restricting this result into the real part, we see that these computations gives us the information, the relevant information, and we can see that this computation should yield the first term only. The other two should disappear. Then we will just assume that those two parts are equal to 0. So the solvability conditions are these two things. Now, for the second condition, actually, we tried for a simple approach. Instead of an nth order differential equation, we can start with second order, and we can show that the second condition is also given on given on this page. You see in the last line, for the second order differential equation, you have these two variables to be given C1 and C0. Okay, then in order to get those results, we should start with the solution of the second order differential equation. We should start with the solution of the second order differential equation. That is 12. And we should check that the imaginary part of Wz integrated over R is equal to C1, and the function itself integrated the imaginary part is integrated, should give you C0. Okay, then we need to see these two conditions are derived directly. These two things should be derived directly. And from the previous page, we get this result easily. And from the second, we have this WZ bar. You should be careful with the computation here. These computations gives you a simple result for the imaginary part of the function. As you see, integrals are over R, small r, and K1 and K2 are disappeared after the integration, just -1 and 1. So if you substitute them in the equation, you will get this thing. Well, in order to get this result, these two terms should be equal to 0. So those are actually added up is equal to 0. So you get IC1 for the first boundary condition or necessary condition. And for the next, we can try the same thing, C0. Now, we want to see the properties of operators. The essential operator we have here is TR tilde K. That is from LP to LP. P is greater than 2. And in this case, we need the solvability condition also in order to discuss the properties of this TR tilde. We should discuss the LP. Well, TR tilde F is equal to this thing, and we need the solvability condition in this part also. The next thing we have is necessarily the discussion of these two lines. That is, K1 and K2 are infinite series, and we have to check what happens to them after a while. Now, you can easily see that these two, K1 and K2, may be treated well. We know TRK is an iterative application of T1. And the result is appearing in this two lines. You can decompose it into two parts for simplicity of the computation. And one of them is T1RK, the other is T2RK. Those are given in here. In the first one, you see that there exists no K. K1 or K2 does not appear there. So we will discuss each operator T1 and T1R and T2RK separately. First of all, differentiating TRK with respect to Z bar of order L will give you these, in these two lines, will give you the TR tilde K minus L again. So we haven't lost any property over there. TRK is defined during the definition. We have used the homogeneous boundary conditions. Those boundary conditions, homogeneous boundary conditions, gives you that the real part of the derivatives of the unknown function is equal to 0, and the imaginary part is equal to 0. And in that case, the solvability condition reduces to this last part. Actually, previously, we have taken T sub dk, that is the operator defined over the unit disk, differentiated with respect to Z bar L times, are compact operators if the L is less than K. Well, this tells you that simply T1RK has the same property. Now, the missing part is T2RK. We will get the derivatives of T2RK with respect to Z bar and discuss the properties of those operators. The important part here is naturally the series we have obtained, K1 and K2. Those series are convergent, and by the Montel theorem, they are holomorphic in Z, in R, with respect to the variable Z. So this is one part of the K1. And if you take the absolute value of that K1, restricted to the absolute set is equal to 1, you will have a simple series which you can give more property than you may expect. You see, K1 in absolute value assumes the maximum in the domain of discussion by 4R over, this is the last part, 4R over by 4R over 1 minus R squared, R plus 1. So this is one part of the discussion, and you can reduce that property, that maximum value, to be less than 4R times 1 minus R squared, 1 plus R. Now, this similar computation for K2 should be done, and K2 is given in the first line here. Take the absolute value of K2 and restrict it to absolute Z is equal to 1, gives you this property. And if you compute the addition of those in terms, you will have this result 4 over 1 minus r squared times a series, but that series may be written as 1 over 1 minus r squared. So we have obtained the maximum value on the boundary of the ring, the maximum value of K1, K2, and the maximum of K1 and K2 is equal to 4 over 1 minus r squared squared. So this gives you that T2 tilde K, T2R tilde K is bounded. Well, then it is compact if L is less than K. Compact if L is less than K. Okay, we substitute that value in here, and we get pi rk. Pi rk is given in the 3-line formula. Naturally, it is from LP to LP, and those are Calderon-Sigmund type strongly singular operators. So pi T2KR, the derivatives of them with respect to ZK of order K is bounded operator. So we get that pi rk from LP to LP, P is greater than 2, is bounded integral operator. Now, we know the properties of the operators, and we can use them in our discussions for the derivation of solutions. Higher order, we will assume here that the equation is higher order linear equation. That is, we have the equation in this page and with number 15, and we will discuss the solutions for this equation. Okay, in this case, we do not want to mix up the boundary conditions into the problem. That is why in here I have taken the differential equation with homogeneous boundary conditions. That is, these number 16 are given here. For the differential equation, you should be careful about the properties. You see, we have 2 different types of coefficients, AML, BML, and Q1J, Q2J. Okay, we have to see what happens to them. AML, BML should be LP, and F should be LP, that is all. Q1J, Q2J are measurable bounded functions, and they should satisfy a property which does not spoil the type of the differential equation. You see, we have started with the elliptic type differential equations. So if the summation j from 1 to k, Q1 and Q2 in absolute is less than 1 Q0, then our need is satisfied. All right, then what we get will be this thing. If we have such a computation, we hope that we can conform the differential equation into an integral equation, singular integral equation. That expectation is given by this lemma. The Schwarz problem, 1516, stated in the annular domain, maybe there is equivalent to the singular integral equation given by 19. Okay. The function g here is actually the application of TRK to G should yield W. That will be necessary at the end of the computation. And we can easily observe this thing. Pi hat RG is given by 20, and K hat RG is given by 21. So I need to check okay. So I need to check what type of symbols I am using in here. Now, if W is equal to TK tilde G, then WZ bar, the differentiation with respect to the WZ bar for the K of W is equal to G. And if you observe the second line, using this information, I can get pi at pi tilde RJ G, and from the second one, we get the conjugated. Similar computations are also valid for the operator T. And in this case, we have these two lines here, and all of them are given for the operators related with the linear differential equation. So we can discuss what happens to 19 we have taken. Actually, what we have seen up to now is the identity operator plus pi hat R and K hat R. Pi hat R are bounded operators. K hat R are compact operators. Okay, then I have a set of this type, and in this set, bounded operator, identity plus the bounded operator pi r hat is invertible if the Q0 is suitably chosen. Q0 is this thing. We can just trace how we can obtain that Q0 here. As you see, Q0 is actually the starting with this inequality, Q0 times maximum of these things gives you the Q0. So that is the maximum of the norm I hat R, as we know. And what we expect here is this norm should be less than 1. And if it is less than 1, identity plus R is invertible. Okay, now we can use the Fredholm alternative after just application, just addition of KR hat. KR hat is a compact operator, and that compact actually we have skipped one computation there, but that is easy. It has 2 parts given previously in Turkey, and T1RK is obtained previously by many articles. The second part is also gives you a bounded operator. We will see it in a minute. So the second part is this thing, and T2 KR is given by this integral. K1 and K2 are analytic functions, and by Montel theorem, they are analytic functions. So the K2 are added up to the compact operator will give you a compact operator. Thus, we have obtained the KR, that is compact operator in LP. Okay. Well, we just have stated that compactness previously, so I will skip this thing. Well, all the things are prepared, just we should give the solvability condition. You know that the solvability condition has an integral over R and some separate terms. Those separate terms are all 0 since we have assumed the homogeneous conditions for the problem. So the solvability condition is reduced into just this integral to be equal to 0. All right, then KR hat is compact. Identity plus K pi R hat plus KR hat is invertible. Actually, the invertible operator identity plus pi R hat and the compact operator KR hat are combined. So this will be a Fredholm alternative, Fredholm operator obtained here. This Fredholm operator has index 0. And if you use the Fredholm alternative, you will get that the integral operator we have converted into the integral operators to ordinary the partial differential equations. That integral operator, that integral equation has a unique solution, since the Prudhomme alternative has just the zero index.